How's that? Okay. Why don't we restart? Yeah, so as I was just saying, there's two general classes of methods, not only at next to leading order, for which this is sort of the basic picture, but also at next to leading order, people have been working out slicing and subtraction methods. And so just to say it in slightly more detail, suppose you have a next to leading order process for some differential cross-section with n jets in the final state, or it could be one vector boson and a few jets or something like that. In any event, you can divide the structure of the next to leading order cross-section into two pieces: the virtual term, which includes the interference of the one-loop amplitude with the tree amplitude, and the real radiative term, like the one we were just treating analytically for Drell-Yan. And then what you want to do is subtract off some approximation d sigma a and put it over here. And ideally, you can do all of these integrals analytically. And the reason you can do it is because this approximation can be constructed in such a way that it's essentially a product of a singular factor, like a collinear splitting kernel, and also take into account soft behavior, with the lower order cross-section. And that's all thanks to the factorization property. So you can basically do the integral over one extra parton and combine and find the same poles that cancel the virtual part, and then set epsilon equal to 0. And that would be the analog of the delta 1 minus z term that we found in Drell-Yan. And then there will also be a real radiative term where, with this subtraction, you can, again, everything is now convergent, and you can set epsilon equal to 0 and do this integral of this difference numerically. Ideally, this subtraction term should match d sigma r pointwise on the n+1 phase space. In some cases at NNLO, people have had subtraction terms that don't really match pointwise, and then you have to be more careful how you choose your phase space points to make sure that the integration converges. But that's a little subtlety. And then the factorization of the differential cross-section allows you to split the integral and rewrite it in terms of leaving behind an n-body integral over the same phase space as the virtual terms. And then within the subtraction methods, there were many different kinds of ones that were constructed. There were some initial results for E plus E minus to 3 jets by Ellis, Ross, and Turano. And then there was an FKS subtraction scheme developed in 1995. And then a little bit later, there was a dipole subtraction method by Catani and Seymour. And this dipole subtraction method is sort of collinear focused. In other words, it thinks about the collinear behavior of the cross-section. It constructs a counterterm which is similar to the Altarelli-Parisi kernel, but it's also incorporates some soft behavior on each side. It's not literally only turned on in this place. It's in effect everywhere in the phase space, but it's supposed to cover or approximate the singularities of the matrix element in roughly in this region, where you're collinear and a piece of the soft emission. On the other hand, you could also start with the soft radiation pattern, which at leading color corresponds, or in general corresponds to sort of emission between two different pairs. and you could add parts of the collinear behavior instead. So there's sort of two strategies for how you partition the fact that collinear and soft smoothly merge into each other, but are really described different ways. One associated with a single hard parton and the other with two. So both of these have been used and also generalized to next to leading order as well. So in slightly more detail, for taking, for example, the dipole subtraction formula, the approximation term is written as an explicit convolution of the Born term with a set of dipoles. And there can be a very large sum of dipoles for complicated processes, because you sort of have n choose 2 different pairs of partons. And we'll see you also need to introduce spectator partons as well in order to handle momentum conservation issues. So then this sum here has a sum over colors. There's also sums over different types of dipoles, and a convolution over a momentum fraction, which is introduced to parameterize the functions here. And then when you do this integral, though, you can split the phase space integration into the n-body integration and an integration over a single variable corresponding to a single divergence of a single particle. And in that way, you can achieve what you want, which is to make this integrated subtraction term look like the Born cross-section up to some convolution. So just slightly more detail. When you construct one of these dipoles, you have two particles that are getting singular, either collinear or one could be soft. And you need to, you would like to rewrite it in terms of some kinematics for n minus 1, if this has n plus 1, for an n-body phase space. But you want your n-body phase space to look like the Born phase space, which means you want this composite momentum ij tilde to be massless. So you have to take two vectors here and combine them into a massless vector. And the other rule is you're not allowed to use complex momenta, so no BCFW shift allowed. Otherwise, that would be the way to do this job. Here you have to use real momenta, but there is a way to define a composite momentum, which Pij tilde, which looks like Pi plus Pj, but is massless. And it's made massless by subtracting off some fraction times a recoil spectator momentum, which can be chosen to be one of the other momenta in the process, or it can be picked fairly arbitrarily. So then but you want to also rescale that momentum so that the sum of the ij tilde plus k tilde is equal to the sum I plus j plus k, similar to, because you want to maintain momentum conservation. So in order to do that, you need to constrain these functions, and they can all be expressed in terms of this variable here, which involves pi dot pj in the numerator. So when the invariant mass between I and j goes to 0, this y goes to 0, and this goes back to just being pi plus pj. But there's also the spectator momentum also allows you to define how collinear I and j are. That is, you need to say that pi dot pj is small compared to something else. And once you've done that, you need to know what fraction I carries. So if you use k as the reference for the collinear limit, that means you take the dot product of pi dot pk and divide it by the sum pj dot pk, pi dot pk, and that defines the momentum fraction even, and this definition holds even outside the collinear limit. So then you get a sum over all of these dipoles. There are some color operators in here which can be evaluated explicitly once you have a color decomposition of your matrix elements for your tree level process on each side. But of course in practice it takes some work to do that evaluation. And then this dipole formula is expressed in terms of these kinematic variables. And this piece here, if yij were small, it would be the same as the PQQ splitting kernel, I think. It's written in a slightly different way, where instead of writing 1 plus z squared over 1 minus z, this has been, part of that has been put over here. And it's also been done in d dimensions. So the singular part here is evaluated in CDR scheme. So in any event, you can do this for all the different types of configurations of quarks and gluons and singularities, and do all the integrals analytically. And so that has been a very, all this stuff has been automated and implemented for about a decade in programs, allowing for all of the real radiation part of the next to leading order calculations to be done. Some of them are done with other schemes like FKS subtraction. In the last remaining minutes, I wanted to step back and just ask a qualitative question, which is, why are these higher order corrections so large? Why is it necessary to go to some ridiculous N3LO accuracy? Over here is the over here is a plot which I showed you at NNLO, which we already know this band is probably not quite in the right place when you go to the next order. But these are huge corrections, 30% at next to leading order. If you look at other collider quantities, for example, the total cross-section for hadrons in E plus E minus, their corrections are much more modest. In that case, the answer is sort of like the Schwinger term, alpha s over pi. Well, alpha converted to alpha s, but it's basically the same form as the Schwinger term. And even, if alpha is a tenth, that's still divided by pi, that would be 3%. So most collider cross-sections are much worse behaved than that. This was the Drell-Yan or Z production case. Over here is Higgs production. Higgs production is even worse in some ways. It has a leading order behavior here, and so the cross-section here is somewhere around 8, and the final result is about 100% larger. And it may still move around slightly, but it'll be a while before anybody computes n to the 4 LO. So, and you can see these error bands were still substantial at n and LO. So basically the series has very big coefficients in it. And, it's not really possible to give one definite answer. There are some answers you can give, at least for the jump between LO and NLO. A lot of that has to do with the fact that leading order parton distributions just don't fit the data very well. If you really evolve them according to leading order, it's fairly arbitrary. So maybe you should worry more about things that happen beyond leading order and just give up on comparing to leading order. And the other thing is that in some cases there's new dynamics or new processes that open up. For example, in W and Z production at the LHC, the leading order channel is QQ bar. But when you go to next to leading order, all of a sudden you can have gluons in the initial state. Remember how much larger the gluon distribution was than the quarks? So you can get very important large corrections from the channels with QG in the initial state. The problem with that explanation is you would think that would mean that the QG channel is large positive. But in fact, in the NLO result, the QG is actually negative, and you get the large contributions from other areas. There's another kind of reason for large corrections, some of which has sometimes been tried to resum. And that correction is that there's one effect that happens when you go from space-like region. So this would be a one-loop correction to deep inelastic scattering. So if you're reading this way, this momentum transfer would be space-like. Whereas for Drell-Yan, this momentum transfer is time-like. And when you go from space-like to time-like, from where you measure the parton distributions to where you use them in a process, there's an analytic continuation. So the momentum invariant goes from being negative, where the amplitude is real, to this channel where now it has a cut, which has an I pi in it. But then there's a divergence, this 1 over epsilon squared, which means that you not only get the I pi, in fact, at order 1 over epsilon, but you get a pi squared at order epsilon of the 0. So if you look at the difference between these two contributions, they really just differ by e to the I pi epsilon. You expand that out, and the epsilon squared term hits this one, and you get a pi squared over 2. And pi being 3, roughly pi squared is 10. So that's a fairly big correction. Of course, it was also there in the E plus E minus cross-section, and it didn't give rise to anything particularly big. So it seems to be more of an issue when you are crossing it from a deep inelastic scattering somehow. I mean, from something that you use in the initial state, that it gives rise to larger corrections. Now, these things are not sort of systematically identifiable as a large parameter. There are some cases where there's an identifiable large logarithm where you can resum leading and subleading logs. And there's actually a huge number of different cases to consider. A large number of them go under the heading of Soft-gluon or Sudakov resummation. And these happen often at some edge of phase space. And for example, they can be similar to the situation that happens in high energy QED, where you have massless charged particles scattering into massless charged particles, and you ask about the probability of producing an electron at exactly the same energy, that is, of not having any photon with energy, with non-zero energy. Or to be more precise, we'll include photons that have energies only below delta E and angles with respect to the electron only below delta E. When you work out this probability, you get a logarithmic divergence in the energy and another one in the angle. And so you get 2 logarithms with respect to these resolving powers. And if you invent a variable in the QCD case that is sort of a combination of delta E and delta theta, you can see that you're going to get something that looks roughly like e to the minus alpha over pi log squared of that variable. In the QED case, the exponentiation is a lot simpler because the soft emissions are independent. Because this photon doesn't have a color, and so this graph is the same if this photon is emitted anywhere with respect to this one. And so exponentiation is much easier to achieve in QED, whereas in the QCD case, it's a little more tricky, at least to identify subleading logarithms too. But the general property of the Sudakov regions, which are sensitive to soft-gluon emission, is that they have a double logarithmic property. At each order in alpha s, you get 2 more logarithms in the given singular variable. And you can typically resum them using various factorization strategies. Now, just to give some examples, I mentioned before that the transverse momentum of the Z, or of a color singlet object in general, could be Z, W, Higgs. Those distributions are not defined near PT equals 0, and they have a distribution which is very roughly of this form. So double log exponentiation. And this has been a big challenge to resum these logarithms to high accuracy. And people are, in the resummation, you talk about subleading logarithms, or LL, instead of LO for fixed order. And people can resum about the third subleading logarithms in this process. And actually, the effects are much more pronounced. So there's also a color factor in here. And the color factor that's relevant is CF for Drell-Yan production, because you are radiating off gluons. And the color factor that comes from squaring this is that factor CF we saw before. So that would be CF for Drell-Yan. And for Higgs, it would be CA. And since this is 3 and this is 4/3, the effects are much bigger for the Higgs case. Not only, so these kinds of double logs also appear in another case. They appear within the total cross-section, although in this case, it's a little hard to connect them to an external variable. In other words, if you produce a heavy state at a Hadron Collider, then because that state's very heavy, it costs a lot to emit additional soft gluons, or even collinear gluons. And since you're paying a price in the phase space for emitting those quantities, there should be some Sudakov logarithm related to that. So while this happens for transverse momentum, and it's called PT resummation, there is also a threshold resummation to resum large logarithms. Now, in principle, you would like the threshold resummation to be when tau goes to 1, where tau is this variable m squared over s, where m could be the mass of the Higgs or the mass of the Drell-Yan pair. On the other hand, tau is actually not very close to 1 in regions where you still have important resummation effects. For example, for the Higgs mass of 125 GeV at the 14 GeV LHC, this mass is about 1/100th of this. And this goes like the square. So if you take 1/100 and square it, tau is 10 to the minus 4. That's pretty far from 1. Why are we talking about large logarithms when tau goes to 1? Well, the reason is that you effectively run out of phase space much faster if the partons that are colliding have a very steep dependence on the invariant mass. To say it another way, normally you want to cancel virtual divergences against real divergences. But the real divergences, where you emit a real gluon, they require you to have slightly bigger energy and slightly bigger x values for the distributions. And therefore, you can get into trouble if the distributions are falling too fast. These, we saw an example of this already in the next to leading order Drell-Yan production, which has a CF in it, and then it has an explicit logarithm here and a plus distribution down here. this singularity is sort of like a logarithm, actually. So it's the first example in a chain of contributions, and the leading such contribution has 2 more logarithms in the numerator, and it also has additional powers of CF corresponding to iterations of additional gluon radiation, which is successively more soft and more collinear than the previous one. And there's a same formula, leading log formula, for the Higgs, except for this replacement of CF to CA, which leads to much greater sensitivity as well as the fact that the structure functions, the gluon and quark distributions, behave quite a bit differently. So Higgs gives you a big factor from color, and then there's another big factor from the steepness of the distributions. So the effects will be larger if the distributions are falling fast. And for the Higgs at the LHC, the relevant x value was about m Higgs divided by the LHC energy, so that was about 1 over 100. Tau was the square of it, or 10 to the minus 4. So you need to find the gluon distribution and see how fast it's falling there. And in contrast, when you look at the W and Z at the tevatron and at the LHC as 2 other examples, you see they're in regions where, well, at least one of the distributions is relatively flat. In the case of the tevatron, these were both valence distributions, so you're supposed to look at the top 2 contributions here. This would be valence up and valence down. Whereas at the LHC, you need to use the anti-up distribution for one of the 2, but it's in a region where there isn't as much difference between them. So because these slopes are lower than these slopes, that's an additional reason why threshold resummation is not so important for, not very important for W and Z production. But for the Higgs, you either need to do a threshold resummation, but even better is to calculate another term in the fixed order series. Now, Sudakov exponentials are usually negative things, but they actually lead to large increases in cross-section here. And the answer is really that because the same suppression happens twice in the extraction of the parton distributions, which are entering, there are large logarithms in defining the parton distributions, and they sort of go the opposite direction from the one from when you combine when you compute the partonic distribution in the Hadron Collider. So there's an opposite sign appearing. Okay, so that brings me to the end of these lectures. I hope I've tried to give you an overview of what life is like at a Hadron Collider and how amplitudes feed into the comparison between theory and experimental data. And one of the things I just wanted to re-emphasize is that the LHC is a very broadband collider. It doesn't operate at a single energy effectively because there are so many different energies of the partons that are colliding. It has an enormous QCD background that has to be understood well and in order to help the experimentalists look underneath it for rarer processes, including Higgs production, but also possible new physics. The fact that we don't have a great idea right now for what the new physics is going to look like. There were some prime contenders that have been searched for, like supersymmetry, and so far all we have is lower bounds. So there's a lot of need not only for maybe more ideas for what forms new physics could take and what needs to be done. Remember, there's this all-important trigger if your new physics doesn't pass the trigger, you'll never see it. So you need to not only think more about what form new physics will take, but also there's need for theory to get more control over a variety of processes, because we don't know which ones are the most important ones yet or where the new physics is lying. This high multiplicity is very difficult beyond NLO. You may need to have better analytic control over very complicated functions like the elliptic polylogs that Johannes talked about. But it's also very tricky to do these real radiative corrections computationally. There's a huge amount of work that's needed, and different skill sets apply in both cases. So there's a team effort that's needed, and maybe some of you will be involved in it in the future. I hope so. Thanks a lot. Any parting shots, questions? Yep.
So if I remember correctly, then there's some current tensions, right, between measurements and predictions. But then when you consider these differences between next to the cube leading order and next to leading order, it could be that there are no problems at all.
Well, yeah, there are different kinds of tensions or anomalies. I don't think there are, at the moment, too many high PT tensions that people are getting that excited about right now. Of course, you know there was maybe some 750 GeV flurry of activity, but the nice thing there is that the LHC was collecting a lot of data. They could go back, collect more. In that case, it was just some coincidental statistical fluctuation, so that's easier. In the case where you've been studying the same thing for a while and the data isn't coming in as fast, then you have to look to other issues. There's like some tensions in the, I showed some tensions in the Drell-Yan distributions or Z rapidity distributions where no particular set fit particularly well. So then you go back and you refit and you ask, can you accommodate all the data? In fact, the PDF fits, they don't typically use a standard chi-squared distribution to assess the goodness of the fit. There are lots of systematic errors in the different data sets that aren't completely accounted for. So, but they're not generally believed to be situations where there's new physics. There's more possible hints of new physics in the B-physics domain right now. There are a few anomalies there, but that's kind of outside the realm of what I was discussing. But there may be more need for a little more precision theory in some of those cases. Some of those anomalies involve distributions that are pretty hard to calculate theoretically. Others correspond to ones that are much firmer ground. Any other questions?
I have one which is actually, I would say, more philosophical.
Okay.
It seems to me that we are kind of chasing higher and higher loop orders every time, and despite knowing that sooner or later this approach has to break down, right? So
Oh, do you mean that the series is asymptotic?
yes.
Okay.
We know that this actually does not converge at the end. So do you think that we will ever be in need of changing our approach because we reach the part where this breakdown manifests itself, or do you think that we can just keep going loop order after loop order and
Yeah, well, the general rule of thumb is that when you have a asymptotic expansion, the place where you should start to see the effects of the non-convergence of the series, you should sort of truncate the expansion at a term which is roughly 1 over alpha. Now, if that holds true, then we should stop at around 10 loops for QCD at momentum transfers of 100 GeV. So, okay, we probably don't have to worry about that yet. But this is kind of a rough guide, so we should keep in mind maybe that was a bit too simple. Now, you can actually get closer to the current value if you just go to momentum transfers where alpha is more like 0.2, 0.3. The tau, I mentioned that measurement of alpha S using tau decays. That's at a very low scale. The mass of the tau is 1.7, but the mass of the hadronic system is quite a bit lower. And so there you have to worry about renormal effects and how you're going to deal with them. I'm not an expert on it, but if you were interested in that topic, I would look for papers on extracting alpha S from the tau. They will presumably discuss these issues. In QED, you can go to 137th order, so what are you waiting for?
We've seen a very skillful walk through the fields of real physics, and I would really like to thank you.